So for the motivation for this, using Python to enter the world of microcontrollers, I'm just curious, who of you is working with IT-related things here? Like monitoring and sensor data, streaming, aggregation. Yeah, there's quite a lot of you. So that is probably the motivation if you're dealing with all these nice solutions at work to do the very same thing at home, right? But that could get very expensive in the very end because, you know, you will use real hardware for that you pay for yourself. And attaching sensors, playing around with these things, bare metal, that can pretty much break things. And that can get quite expensive. And even the electricity bill is a thing. Probably not at work. Hardly any one of you has noticed or what your employer is paying for electricity, but at home you do. So you might consider these things. So using microcontrollers, what exactly is a microcontroller? Well, it's pretty simply a combination of CPU, memory, storage, and I/O, and that's all on the same die. So if you have these things in a computer as regular components, aggregated in some way, this time it's all on a single die in a single controller. And it's very energy efficient, it's cheap, and it's quite powerful these days, as we'll see in a minute. A few words about the history. So to the left is the first available CPU, the famous Intel 4004 from 1971, and to the right, the Texas Instruments, the TMS 1000 from 1976, which is already that very mentioned combination of a CPU, 4-bit CPU at 400 kilohertz, and some ROM and some RAM and some I/O, like counters, registers, timers, these things. And today, we have quite powerful platforms, so quite capable resources. The typical scaler to use compared to the beforehand, which was the K for kilobytes or kilohertz, is now the M for megahertz and megabyte. And we have some examples here. The probably most used microcontrollers in the maker scene, the ESP32 family, quite capable, 32-bit single or even multi-core CPU, 160 to 240 megahertz, already has megabyte range of RAM and ROM, quite capable of extending these platforms. There's a large variety of models on the market. And in the middle, there is the STM32 platform. This especially is the Pi board, where all the MicroPython stuff originated from in the project Cortex M7 CPU, 260 megahertz, also in the megabyte range of RAM and ROM, and loads of I/O. And to the right, one of the most capable platforms currently on the market for the price, the Raspberry Pi 2350. Here, it's just the single chip there, and here placed on the commercially available Pico 2W, even with Wi-Fi. And that already has a dual Cortex M33, and at boot time you can decide if you would like to use the ARM platform or RISC-V platform to execute. Has dedicated I/O and also the same range, all in megahertz and megabyte. And there's also blurry lines here when you compare to the normal computers and the microcontrollers on the low end, and things get quite blurry currently because we have the Raspberry Pi, small-sized computer actually, but there's a spin-off, the Compute Module 5, and that has pretty much the idea of a microcontroller actually. It's a board with that computer and a GPU and RAM and Wi-Fi attached, I/O attached. It's not on the same die, but it's a small factor you can integrate somewhere else. So it's no longer that hard line between these platforms. And down below there is, from DF Robot, the Unihiker, the M10, which is comparable to a Raspberry Pi, has a lot of hardware on it, a Rockchip CPU, display, some sensors for an IMU, loads of I/O, also in the megabyte range from the performance, pretty much comparable to a Raspberry Pi 3, and a pretty well-done infrastructure around it. So if you buy these things, you can attach it to a computer. It already configures you a network interface via USB-C, It has a Jupyter notebook running. You can directly attach to it and just play around with everything. And documentation is quite good on these things. It's a lot of fun. So if you want to see one of these devices, I have one with me. You can have a look at it later on. And to the right, there is the smaller version of it, the ESP32 based, this microcontroller platform, but pretty much the same idea. So these platforms should look very comparable, and they have different price ranges. Well, the left one is around 100 euros, the right one is in the 30 euros range. So what it actually was doing coding for microcontrollers. So the hardware-wise, it was a very simple system, like in the good old computer days with the C64. Who has used the C64? Who is as old? Oh, my dear. And with this very, very limited resources, they have to be carefully managed. Remember that scalar to use was the K, like in kilobytes and kilohertz. It had the ability to just run a single task. There was no multitasking thing around. It's just that one thing that you execute, nothing else. And coding was done in low-level languages like assembly language and C. Who is familiar with assembly language programming? Yeah, that very much. The experience level necessary for having fun was very skilled and expert or senior level at that time. So why that, you ask? Well, actually, it is all about ensuring real-time capabilities. You have to guarantee things to happen at a specific time or exactly periodically, absolutely always. And that is not something you do on regular computers. There's just, you think it will happen at some point in time, and near that very point in time, it is going to happen, but not exactly then. And for microcontroller applications like used in the automotive industry, that is not a thing. It has to happen exactly at that point. So you have to take care of these things, and you have to mimic multi-threading, because you have just that single task that you can execute, but there are many other work packages to be done on that microcontroller. So you have to find a way how to do this on that single core that you can use, and that is by mimicking multi-threading. So allowing different things to happen concurrently by interleaved execution of chunks of algorithms. And that is really top-notch corner of capabilities for software engineers. So how does it look like? So to the left is a simple algorithm, all done in Python, with a very simple task. Who has an idea of what that algorithm is doing, where this is going? No one. So be patient. And to the right one, so it's just having some number, spending some iterations on calculating a formula, squaring that number, adding the original number, and then after some iterations, look if this will pass a certain threshold. If that's the case, stop it and take care of the number of iterations, and maybe go on with other numbers to see how they behave. And there are quite some numbers with some interesting behavior behind it. And to the right is an excerpt how you would do it on the microcontroller. If you were to guarantee real-time capabilities, then you have to take care of how long an execution really takes and how much of the execution of the algorithm you can do in a time cycle. And that's what I'm trying to simulate here. So see, you have some RAM available, like the registers that I prepared, and there is a program counter. That's the main thing a computer uses to run your code. It's increasing a program counter and looks what's up next to do. And then I'm reformulating that algorithm to the left in an endless loop and looking at where I am currently with the program counter, just execute parts of my algorithm, like just load the variables from register that I can use them, and in the next time cycle I'm assigning that variable to another temporary variable. In the next cycle I'm doing the squaring, in the next cycle I'm doing adding the original number, and then I do compare. And comparing means actually as a reference to one of the other well-done talks that we have with the exceptions who are sophisticated go-tos. That is actually how it really works here in this mimicking assembly language, where you decrease the program counter to get in the state where you have been once before to mimic that loop behavior. So you're at the point that you should repeat things, and how can you repeat things? Well, change the state to a state that you were in before, and then things repeat. And if that's not the case, then you can bail out and have the very same thing. But with this approach, you can really guarantee that these things happen at the very specific time point, because it's just that one time cycle that you have for executing that job. So what it kind of gets these days, it's a very complex piece of hardware with easy access, quite capable resources. Remember, we're talking megabytes and megahertz these days. Microcontrollers are no longer really bare metal. They have an operating system, although most people don't notice, because no one is hardly, if it has a Wi-Fi chip on it, no one is programming the registers of the Wi-Fi chip to get the connection. It's just you have a command set that enables you Wi-Fi, and then you're happy in using Wi-Fi, and that's it. And that's what operating systems on microcontrollers really do for you. They are multi-threading capable, and coding is done in high-level languages like C++ or Rust. There are dedicated IDEs available, which support you in implementing that very complex behavior so that you don't need really to take care of. And it's often provided by the vendor, but there might be a vendor lock-in down the road. But that's a different story. It addresses entry-level and average users, so Arduino paved the way here. And even no-code development platforms exist. In your browser, you're just moving blocks around and have you lose and get things done. And machine learning is coming to the microcontroller. That's already a tough thing. And Python is here. So what MicroPython offers, it's very simple to learn. We have very much the same feeling for use on the microcontroller than we have on the regular computer. High-level functionality is available, like requests. There's even NumPy available on the microcontroller, so you can do vector math on it, matrix multiplications to your liking. There's SciPy, there's OpenCV for simple machine learning tasks or image recognition tasks that will work. TensorFlow is there, and there is CircuitPython. Well, big shout out to Adafruit. They made a whole ecosystem around all these chips that are available that make it so easy to connect to your microcontroller and MicroPython. Just use them. And it lets you focus on the problem, not the implementation. That's the Python thing, I guess, the most important thing, that you can think about your problem, not how to formulate things. Because, it's preferably only just one way to do it. So the difference to computers and microcontrollers: computers designed for multi-user, multitasking usage, always need to be ready for unforeseeable usage. And energy saving is usually done by clocking down your CPU. And on the microcontroller, they are just focusing on a single task, really. They can enter sleep modes when not in use. And that is a huge potential for energy saving. So it changes the way you need to think in implementing periodical tasks. How would that look like? So on a computer, the usual thing and very simple formulation is forever read from a sensor, do something with the sensor, like sending it somewhere, and then sleep sometime. And that sleeping sometime allows other applications to run and do things. And on the microcontroller, it's really different. The whole formulation gets, my microcontroller is in some sleep state, and it wakes up, it boots, and at boot time, it reads the sensor, does something with it, and configures a way to get to sleep and wake up again by setting an interrupt, timer-based, say for 10 seconds, and then it goes in a deep sleep mode. And after that, an interrupt gets fired, it wakes up again, does the same thing. It completely changes the way your for loop or your while loop is really working. And it is working just because it has just this one single task to work on. And that is ideal for battery usage, because that really, these deep sleep modes and microcontrollers allow you to get down to microampere level of usage. And then with a single battery, that thing can run for months. So let's start in real coding, the hello world for microcontrollers. No, actually, we're not going to do this today. That is usually the blinking LEDs example, and where you can get with. If you come from the Raspberry Pi, it's pretty much the same thing. using a GPI, turning it on, turning it off, getting a high state, low state, that makes your LED blink boring. But regarding performance, the famous thing, will it actually run, and you probably know where this is going if you know my talks actually, can it run calculation of the Mandelbrot set? And that is actually the example that we've seen earlier in the code. That is exactly what was happening there for each and every pixel. So for those who are not familiar with that, there's the complex plane of numbers, and you can choose any number, do that very calculation on it, like squaring it, adding the original number, and then see where the result goes to. If it bails out very quickly, so it hardly takes any iterations, you would color it, coloring with, in this example, an A, for example, or a B if it takes a bit longer, or a C if it takes even longer, and the white parts in the very middle is where you can't decide because funny things happen. You should do it in your head or with your computer implementing. It's quite fun. And that is a quite compute-intensive task, actually, and these days microcontrollers can just do it in no piece of time. It's just, this takes you hardly a tenth of a second to compute. And that's because, microcontrollers are very small things, really, but they're very capable these days. So the microcontrollers we're talking today have the performance of Pentium computers years back, and that is quite a thing. We're talking 200 megahertz. Megahertz, that's a lot. So home lab tasks. I had an interest, getting back to the very beginning, for the motivation to do these things that we do at work at home. And for me, it was monitoring power usage, or gas usage for heating, or temperature controls, and all these things, or even solar revenue. And there are some ways to do this, like directly measure the solar inverter, or at a special power monitoring device like the Shelly Pro, or use the infrared interface of the main power meter. Let's have a look at that. So here to the right is my old power meter. So that's a typical setup. It's not a smart one, although many people call it already smart because it's digital. That's a typical digital power meter. No longer, sadly, no longer the old Ferraris effect-based old analog meters, but the digital one. And to the right, top corner there is this famous infrared eye. So it's an optical interface which talks to you, if you know how it talks to you. And in this way, this model talks the D0 protocol. It's really just a serial interface you can attach to. You just need a photoresistor and a phototransistor and a resistor. Attach the resistor to supply voltage and the phototransistor to your ground, and the optical interface properly placed will then switch the transistor on and off, which gives you the data stream that you can read from your serial interface. That's quite simple. And below that photo is what you get. And that looks complicated, although it really isn't. The D0 protocol is well documented, and the simple things we want to look at are clearly visible to the human. It's the part at the bottom, these numbers, it's the OBIS protocol that you can see this, an object identification system language, and we would be looking for the 10181 part of it, and there is this 40,000-ish value, and that's the value in kilowatt hours at that very specific point in time. So all you need to do is really like match these patterns, regular expression, or search for it, and then parse it, and then have it done with a time step. That's it. And then they replaced it at the very end of the March, and I've got the new one, and there you can see how that really looks like, a 3D print, and just that phototransistor and the resistor. That's really all you need to have. But that thing talks a different language, and it was a lot more challenging. To the left is what it looks like now. So there's hardly any human-readable thing. But not all is lost. There is structure in it. There's a byte stream of 1Bs and 0-1s, and that already gives you a hint. So if you're working these things a bit, if you work yourself into these things, then you see that this might be a hint for what protocol is used. And this time it's the SML language. And the SML language can be worked on. So the SML protocol is basically a list of messages, and there is an opening and a closing sequence. So the list of the 4 1Bs and the 4 1s, that's really the opening sequence, and 4 1Bs and the 1A, that shows you that you have the closing sequence. And anything in between is a byte stream that you can pass. And this byte stream always starts with a single byte that shows you what data type to expect next and the size of it. And that can be a list, so a list of more messages, and it tells you how many items there are on the list. And then it tells you that what type to expect, like a string or an integer, unsigned or signed or whatever, and what size that thing is. And then you can go on. Write a parser for this. Probably a recursion-based parser would be the neatest thing to do. That's what I actually did, and the output of this looks like this. And there's that one sequence that is really key, where the same value can be found that I was looking for with the old power meter, and there we had a list entry with 7 entries to process, and there is a byte string at the very beginning to look for, to match really, and that is again the identifier of the obis value, this time in binary, as a byte stream, and then there's some filling bytes, and then there's the value 30 as a byte that indicates that we have the unit of watt hours to expect. And then there is a value of 3 that gives you the scalar, so whatever value is really there needs to be multiplied by 10 to this very number to the power of 3, so 1,000, and the value was 22, so we are at 22 kilowatt hours. And then we're done again. It's just add the timestamp, and then you can do the very same things. So how does it look like? This is for the old power meter readings, because the new power meter reading has a coarser resolution currently. You can increase it yourself if you have a good provider that tells you the pin. Then you use your some headlight or something to really get this into your system optically by blinking, and then you can reconfigure the power meter. It's a great interface, really. Me and my provider, we are not at that point currently. So we're tackling about this. Very curious, so this is the old thing, and in the very middle, between 9 and 12 o'clock, you can see a straight line at 0, and that's the typical German behavior. You have a balcony power plant, then your usage drops down to 0, although you're already backfeeding, but you don't get any revenue for this, and you don't save anything. It's just that you have no power usage. And down is the energy over the course of the day, and to the right is the costs behind it. So in a probably March day was 2.5 euros for my electricity bill for the day. And with a plateau in the middle, I can start fiddling around with numbers to see if a battery would make sense for me in the very end. Yeah, so now we are near the end. The key takeaways for this: Python applications can easily be transferred from a microcontroller thanks to MicroPython. It's just all the same. If you're very familiar and simple concepts in Python, you're good to go on a microcontroller. In case of cost and size of the device is key. This can be quite trivial. Copy, use it. When energy saving is the main goal, then the way to handle loops is key. You have to rethink how you do your work, so that you can send that device to sleep whenever possible and keep it there as long as possible, and wake up by events like timers, device movement, pin state changes, these things. And have a close look at using Wi-Fi, because reconfiguring Wi-Fi frequently costs a lot of energy. So if you let your device go to sleep and your aim is reading a sensor and then sending the data over Wi-Fi to some server to process, then you have to reconfigure your Wi-Fi for this every time, and that really costs you a lot of energy. And this is why devices like the ESP32 have dedicated ways to keep your Wi-Fi in some sort online where the rest is going to sleep. So it always pings after a few seconds that it's still there to keep that connection alive, and that really doesn't cost you a lot of energy, and the rest of the chip is going down in deep sleep mode. Then we are not really at microamps anymore, but it's milliamps anymore. Pay attention to monitoring battery voltage. Yeah, if you have a battery-based device, then batteries drain. At some point they empty. You want to be monitoring this. It's when it's a good time to replace these things. And there are even vendors who take care of that. Has bad ideas for this, sadly, by just using a set of resistors in series, and in the middle pin you can really grab the voltage level then and monitor this with the ADC that you have on the microcontroller. But this series of resistors drains the battery. That's a really sad story, really, because the idea was right, and it was just one transistor missing to get it really correctly. But here we are. So with this, I'm at the end of my talk. And just can you leave you with questions, and thank you for your time.
Thank you, Jens. That was an amazing talk, and I'm sure the audience has so many questions for you. Please post your questions in Slido. And yeah, we have still plenty of time to look at the questions. Please. So we have one question from Anonymous. How is the analog phototransistor output converted to bytes?
Okay, so what you're using is the phototransistor in series with the resistor, attach the resistor to the supply voltage, 3.3 volts usually, and the rest is going to ground. And then the phototransistor, if it receives light, will pull that pin down. And if there's no light anymore, then it will pull up again. And this pulling down, pulling up is giving you the bits that make the byte stream that you can really read on the serial interface. So consider that the other side is just having a serial interface, and instead of connecting electrically, it's doing this by an infrared LED.
Great. Another question is the protocol of the second device not open publicly?
Oh, it's totally open. Actually, the BSI has written a document with hundreds of pages on it. And it's linked in the talk. The talk is on my GitHub.
Good. Another question is there an alternative to Wi-Fi? I can't connect to anything in my basement, and someone is concerned.
When it comes to long range in-house, it can be difficult not to use Wi-Fi. So the usual suspects is Bluetooth. That won't help you really for long distances. Another alternative is LoRa. That will work in-house probably, and also out of the house with not a lot of data to be transferred. That are options. Else, repeaters, I guess. Power line bridges.
Okay. What can you say about the compatibility of MicroPython with modern mainstream microcontrollers?
With modern mainstream microcontrollers like those that I have shown, that way would be perfectly compatible because of the way the MicroPython is developed on these things. They are more powerful, probably, used in professional areas. And, well, there's a broad range, really, of capabilities. Have a look at the MicroPython homepage. There's a huge list of microcontrollers that just work. The documentation is complete for getting in touch with these things, how to start, how to get MicroPython on that very microcontroller. It's darn simple these days, really, to get it done. And probably the PyCon W, the Raspberry Pi version, is by far the easiest thing. You can't break it. You attach it to your computer. It shows up as a mass storage device. You copy the firmware, the MicroPython firmware on it. Afterwards, it will reboot, and then you have a MicroPython device. And then there is another tool called MP Remote, and that is your bridge from your computer to that very microcontroller. You can mount your local file system on the microcontroller, so you don't even have to transfer all the libraries for the development cycle to that microcontroller. Just use it and play around with it. That is a fantastic world to play interactively and develop.
Great. Is there also a MicroPython implementation for PC so you can write 100% compatible code there?
Absolutely, yeah. You can even run MicroPython bare metal on the Raspberry Pi. That is possible, yeah.
Okay.
And there are subtle differences, really. So it's Python, and not all of the standard library is covered, though. So all the very exotic and hardware-consuming things in the Python standard library are probably missing. There might be simple implementations. The API is very, very comparable, and I think magic things can still happen using MicroPython. Optimizing for a microcontroller involves, again, the old thinking to handle resources.
Good. We still have 2 more questions, or 3, because we still have plenty of time. Can you combine the Python code for the ease functionality of more complex computations with the microcontroller code for battery efficiency?
Can I combine these? Or
can you combine the Python code for the ease of functionality of more complex computations with the microcontroller code for battery efficiency?
Yes, so battery efficiency is all about saving compute power, so doing computation-intensive things is possible on a microcontroller, but you should do that seldomly, so not very often. Else the microcontroller wouldn't be the right choice. Then if it's compute-heavy, if it's compute-intensive what you're up to be doing, then Raspberry Pi, real computer, or separate the tasks. So sensor, readout, microcontroller, send the data to some device that is always online at your home, at your lab, virtual machine, some things, let it do the compute there, and use the microcontroller just for the simple things. And else is do your compute-intensive tasks and get the microcontroller to sleep again as long as possible. So for example, with my new power meter would be, it's sending these data, the new time tags, every second. But with that resolution, it hardly makes sense to look every second to receive the same number again. So in this case, I would really change that code of monitoring to not continuously watch my serial interface, but just have one data tag and go down to sleep for another minute or even 5 minutes, and then come back and see what changed. And that for this device and this configuration is good enough a solution. For the old one, that wouldn't be a different story, because the resolution would have been better, like watt hours, not kilowatt hours.
Good. I think we can take one more question. What typical optimization steps can I take for loops?
So if it comes to battery usage, then it's not using for loops, but do your task, get to sleep, set a timer for rebooting. So that makes your loop. And if you want to really have a more efficient loop, then you have to think a bit different. Like we are used to have, for example, in a for loop, the range generator, which generates each and every number one in a row, which is very efficient because it's not having that large list of numbers in memory that you can work on. Just generates that number. And on the microcontroller, it's funnily the opposite. It's the better idea to generate the list of numbers and iterate on them, because this is faster, and faster in that case can be more efficient. So if you have room for storing all your numbers, do it and just call them. Range works, but list range would be the better idea.
Great. We don't have any more time for more questions. Can you please thank Jens one more time for his amazing presentation?